Okay, I've actually managed to get quite a bit ahead, plus I'm changing some stuff. 3.5, I'm changing the assignment considerably. Okay, 3.5 was originally 1 to 31 odd. We're going to skip problem 11, and we're going to skip 23 and on. Okay, so maybe I didn't aim this right. Aiming it over here. This is 3.5, okay? 3.5. 3.5, it said 1 to 31 odd. Skip 11, skip 23 on. Now, I actually only had one more problem to do from 3.4. Then I can get started with 3.5. I am considerably ahead, as it turns out. So what I think I'll do for today, I mean, if I finish 3.4 pretty easily today, I only have 2 more sections, 3.5, 3.6, and I still have all of this week for 3.5 and 3.6. All right. So I'm probably going to finish my formal lecture early today, in which case I'll let you ask questions. So maybe as a heads up, I'll be done sort of early today. And then you have a choice. I can turn it into an office hour where if you want to go back and ask me stuff from, you know, from any of these, you may. But if you don't have any questions, we can just end early. And I'm guessing that's going to be true for the next couple of days also. I am ahead now. I've managed to get a little bit ahead. Okay, but again, I like to be ahead in case something goes wrong again, my computer goes down, I get sick or whatnot. Okay, we will have a quiz on Friday. And whoops, I'm over here. Okay, so again, our next exam, we're aiming for the 9th of October. Okay. And if I get ahead and I'm able to, I'll just go ahead and get started with chapter 4 if it comes down to that, but we'll see how it goes. Okay. All right, so I'll probably be finished a little early today. You think to yourself, are there any questions that you might want to ask from anything up to now, which is 3.1, 3.2, 3, and 4? But if you don't, we can just end early. And that'll probably be the same for tomorrow. That'll probably be the same thing for Thursday also. Okay. All right, so we'll see how that goes. All right, so back to 3.4, these rational functions. I was going to do for you number 39. Okay, so I did 37 yesterday. So let's look at the directions again. Okay, so sketch the graph of the function and label the slant asymptote. Okay, so there's going to be some slanted asymptote for this one. Okay. All right. Okay, x squared plus x minus 2 over x plus 1. Okay, first I'm going to factor. This factors into x minus 1, x plus 2 over x plus 1. Right? X squared is x times x. How do I get 2? 1 times 2. We want to have a positive x, so positive with a 2 and a negative 1. And nothing cancels out, so we have it. Okay, now we peek back at the notes we had yesterday, right? We will have a slant asymptote if the degree of the numerator is 1 more, and when we say 1 more, exactly 1 more than the degree of the denominator. So like this one is x cubed, this is x squared, 3 and 2. So you'll have a slant asymptote, 7 and 6. Okay, the one I did yesterday, number 37, x squared, x to the 1. So there's a slant asymptote. This one, x squared, x to the 1. So we will have a slant asymptote. So the first thing we're going to do is find the slant asymptote. You can do that by long division or by synthetic division. Okay, so I'm going to take x squared plus x minus 2 and divide it by x plus 1. If I do synthetic division, do you recall when I put my synthetic division, I don't put the 1. Remember what I put instead? Negative 1. You change this sign here when you do the synthetic division. Here, I just put the coefficients, 1, 1, negative 2. So this 1 corresponds to x squared. This 1 corresponds to x. This -2 is the constant. And x plus 1 means I put -1 here. All right, 1 comes straight down. And then you multiply and add, and so on. So multiply, -1. Add, 0. Multiply, well, 0 times anything is 0. Add, -2. All right, so x squared plus x minus 2 divided by x plus 1 is equal to x minus 2 over x plus 1. All right, so y equals x becomes the slant asymptote. Okay, you just ignore this fractional part. Okay? If you remember what we did yesterday, you ignore this fractional part and say y equals x plus 1 becomes the slant asymptote. The logic being, if you plug in this 1 over x minus 1 from yesterday, if you plug in a super big positive number or a super big negative number, this drops to 0. So it's essentially y equals x plus 1. So when I go way out toward infinity, or when I go way out toward negative infinity, you get real close to the line y equals x plus 1. Okay, same logic here. Okay, if x is really, really big, this is like 0. Or if x is a big negative, -1 billion, this is like 0. So we get real close to y equals x. So y equals x, we know it's a slope of 1 going up at a 45-degree angle. Okay. So the graph gets really, really close to y equals x when x is way out there and when x is way out there, but not near the origin, so to speak. All right, so now we analyze this. We can get our intercepts pretty easily. Okay, what happens when you plug in 0 for x? 0 there, 0 there, 0 there. Well, 1, 2, 3. If these 3's are 0, you might as well pretend it's not there. So it's like -2 over 1, which is -2. So that gives me 0, comma, -2. And now I say y equals 0. So y, again, where's y? I don't see y. Well, f of x is y. So I put a 0 right here. And remember, when is a fraction equal to 0? A fraction is 0 when the top, the numerator, is 0. So I just look at this. So what number makes this 0? 1. What number makes this expression 0? -2. So I have 1, comma 0, and -2, comma 0. So this is what I have right now. All right, so I have a vertical asymptote at x equals -1. Okay, so vertical asymptote, x equals -1. Right here. And now I'll do my sign analysis for x approaches -1 from the left, x approaches -1 from the right. So a little bit to the left of -1, like -1.1. Right? So I rewrote it here. Okay, I'm going to plug in -1.1. Clearly, I don't want to find the exact value. I just want the sign. So -1.1 subtract 1. That's a negative. -1.1 plus 2. That's a positive. -1.1 plus 1. -1.1 plus 1. That's a negative. In fact, it's a very small negative. Remember, when you divide by a small number, it becomes very big. So let's see. I have a negative times a positive divided by a negative. 2 negatives makes a positive. So y approaches infinity. Right? So when x approaches -1 coming from the left side, I come on this side, y shoots up to infinity. And now x approaches -1 coming from the right side. So if I come from this side, what happens to the y values? Okay, a number a little bit to the right of -1 would be like -0.9. Again, that plus doesn't mean it's a positive number. It means coming from the right side. A little bit to the right of -1 would be like -0.9. Okay, -0.9 minus 1. Negative. -0.9 plus 2. Positive. -0.9 plus 1. Well, that's positive, and it's a very small positive, so this will make the whole number big. Okay, so I have a negative times a positive divided by positive. that's a negative. So y approaches negative infinity. All right, so we got the whole graph. The graph touches here, here, and here. Those are my intercepts. On this side, we get close to the asymptote x equals -1. It goes to infinity. On this side, we get close to -1. It goes toward the asymptote toward negative infinity. And way out here, we approach y equals x. And way out here, we approach y equals x. So the graph looks something like this now. And there we go. All right, so that's as much as I was going to do from 3.4. Okay, I'll get started with some of 3.5, but not too much, since I am a little bit ahead now. Okay, now 3.5, I decided to skip a lot of the stuff. I mean, we are taking pre-calculus, which is a preparation for calculus. Now, 3.5, you say, what are we skipping? Am I getting cheated out of my education? No, it's much more difficult than anything you would actually get in calculus, some of the stuff. Okay, so I'm throwing out the stuff. I mean, it's supposed to be pre-calculus. Okay, some of the problems go way over and beyond the call of duty, and you won't see those kind of problems in calculus. So that's why I decided to throw a lot of these problems out. Okay, so in 3.5, the title is Other Algebraic Functions. All right, we're going to do some graphs of these, but not many. Okay, and I'll show you the problems from that also. Maybe just a quick reminder. Yeah, I'll do it again. Yes, you probably noticed I'm very redundant. I do a lot of stuff many times in case you don't get it the first time. So let's see, 3.4, those pictures there. 3.4, pictures there. This is for those of you that don't ever intend on getting the book and you just want to go off of the video. Just look at the video for the homework problems. There. That should be enough. Here. And there. Okay. Okay, and 3.5. Let me show you the problems there. All right. See, we have some pretty weird square root functions. And you say, what are we skipping? We're skipping graphs of some of these. The graphs of some of these are really, really weird. And even when you get to calculus, you probably don't want to touch a lot of these. Okay, so I decided, well, you're not going to see it in calculus. This is pre-calculus, so why should I give it to you? All right, so 3.5 homework on page 175. So there's that if you need it. Okay, next page. Let's see, we're not doing any of these graphs. Okay, I decided to throw those out. So the ones at the bottom here, these, and I believe that might be it, but I'll give this to you anyway. Okay. Yeah, okay. So we are going to do some graphs, but not many. So the first problems involve domain. We've seen that theme before, all right? So I'll do some domain problems, and that was all I was going to do today. Now you see we got some square roots, and we already know the name of the game. When you have square roots, the thing underneath the square root has to be greater than or equal to 0. Okay. There are some surprising twists to some of these, though, which is the reason why we're visiting them again. Okay, 11, which we're skipping, is matching. We're doing some matching. I decided to throw those out. Okay, the graphs get very weird. So I'll show you what we're not doing. Okay, very, very interesting graphs, but and over and beyond the call of duty. All right, so let's do some of these. Determine the domain of the function. So it looks like all of these have square roots. So the thing underneath the square root has to be greater than or equal to 0. You know that, right? All right, so how about I'll start off by showing you number 3. Okay, page 175, number 3, 3.5. As usual, ignore any date that's there. I guess if you go by the date, we're a little bit ahead, because last time I taught this, it was already October, so we're a few days before October. So, but anyway. F of x equals the square root of x squared, x minus 1 squared times x plus 2. Find the domain. Okay, we're not going to graph these, only consider the domain. All right, so you know the way the game works. Anything under the square root has to be greater than or equal to 0. Okay, so I just copy the stuff underneath the square root and make it greater than or equal to 0. All right, so x minus 1 squared times x plus 2 greater than or equal to 0. All right, so I first lay down my zeros, which are 1 and negative 2, right? What makes the expression 0? Well, 1 and a negative 2. And x minus 1 is a 0. X equals 1 is a 0 of multiplicity 2. Remember that language? Multiplicity 2. All right, so I put down negative 2 and 1. And for the time being, pretend you don't know that these are shaded. They are both closed circles. Why are they closed circles? If I plug in 1, put a 1 here and a 1 here. Well, 1 minus 1 is 0. 0 squared is 0. 0 times whatever that is 0. It would say 0 is greater than or equal to 0. That's true. Likewise, when I plug in negative 2 here and here, well, negative 2 plus 2 is 0. So 0 times whatever that is also 0. Again, it says 0 is greater than or equal to 0. Closed circle. Okay. And notice if I didn't have that line underneath it, if it was just strictly greater than, then when I plugged in either negative 2 or 1, it would say 0 is greater than 0. And that's false. So both of those would be open. All right, so we've played this game before. Pick a number in each of these regions, region 1, 2, and 3. So something to the left of negative 2, negative 3. Something in between, 0. Something to the right of 1, 2. Okay, so I'm plugging in here, and I noticed something. And you should always play this trick to make things easier. I have blah, blah, blah squared. As soon as you see the square, what does that tell you about the sign? Automatically positive, right? Unless you plug in 1, but we're not plugging in 1. We already did it. Okay? So I immediately put plus, plus, plus right away. These 3 pluses correspond to x minus 1 squared. It doesn't matter if I plug in negative 3 or 0 or 2. It doesn't matter if I plug in a positive or negative. I'm squaring it, right? So once you square it, all of these are automatically positive. Okay, so the sign is completely determined by the x plus 2. Okay, so x plus 2. If I plug in negative 3, negative 3 plus 2, negative. So that gives me a positive times a negative, which is negative. Is a negative greater than or equal to 0? No, it isn't. So false. So don't shade in region 1. Now, region 2, 0. We already got the plus, right? This plus right here corresponds to x minus 1 squared. Okay, now I plug in 0. 0 plus 2, positive. Positive times a positive is positive. Is a positive greater than or equal to 0? Yes, that's true. Shade in region 2. And plug in 2. We already know this was positive. 2 plus 2, positive. Positive times a positive is positive. Positive greater than or equal to 0, true. Shade in this region. Okay. Now, one of the reasons why I want to emphasize this one is some of you were starting to come to the conclusion that, oh, I know, the way it always works is once one of these is shaded, the next one is not shaded. Okay. That did happen a lot. Okay. In other words, some of you said, oh, if region 1 is not shaded, that means this is shaded and this one is not shaded. You say that happens a lot. Yes, that happens a lot, but not all the time. Or maybe some of you were noticing, oh yeah, if this one is shaded, that means the next one is not shaded, and this one is shaded. Okay, that does happen a lot, but that does not happen all the time. As you can see here, it did not happen. All right, so I got 2 back-to-back trues, and this one was a false. So don't automatically assume that they alternate, like, you know, true, false, every region I go. It does happen a lot, but it doesn't happen all the time. All right, so I'm shading all of this. Now, you don't need to do any union stuff with this one. You can just immediately write this whole thing as bracket -2 infinity. Okay. I don't have to break it into two pieces. Like pretend you had regions 1 and 3, right? Then you would have to do the union stuff. You'd have to do this thing, union, this thing. But there is a way to write both regions 2 and 3 combined in just one overall region. That would be bracket -2 to infinity. So since you can, there's no reason to do the U for union stuff. All right. Okay, then I'm going to show you number 5. Okay. Then after I do number 5, I was actually done, folks. So what is it? It's not even 9:35 yet. Okay, so we'll probably be finished soon. So again, it's up to you. If you want to start asking me questions about previous material, you may, but if not, we can end early. Okay. So f of x equals this big monstrosity. But whatever that big monstrosity is that I'm covering up, there it is. It has to be greater than or equal to 0. Right? So I just copy all that, x plus 1, x minus 3, x plus 4. X plus 1, x minus 3, x plus 4, greater than or equal to 0. Okay, so that means you get the zeros, which are going to be, what makes the 0? -1, 3, and -4. -1, 3, and -4. Okay, so there they are, -1, 3, and -4. Okay, pretend you don't know the shading yet. They are all closed circles because I'm including the line there. More strictly speaking, the logic is if I plug in -1, -1 there, -1 there, -1 there. Well, -1 plus 1 is 0. So 0 times these two guys is 0. It will say 0 is greater than or equal to 0. They will all do the same thing. Okay, like I'll just do one more. 3. Plug in 3 here, 3 here, 3 here. But look at what happens when you plug in 3 here. What's 3 minus 3? 0. So 0 times that is 0, then times that is 0. Again, it will say 0 is greater than or equal to 0. True. So all 3 of these are closed circles. All right, so if I have these, ignore the shading. I have 4 regions. 3 points, 4 regions, right? To the left of -4, I don't have any more hands, but it's there. Between -4 and -1, between -1 and 3, and then bigger than 3. Okay, so just pick a number in each region and plug in. So region 1, something to the left of -4, -5. Something in region 2 between -4 and -1, oh, -2, -3, something like that. Something between -1 and 3, well, 0. Always pick 0 whenever you can, right? Because 0 is usually easier to do math on. And something to the right of 3, 4. In case you're wondering, yes, you can put 5, you can put 6, you can put 80, you can put 1,000,000. But, you know, that just makes the calculation more difficult, perhaps. Okay, so take each of these, plug in. I only need the sign. Okay, so just consider the sign. Okay, -5 plus 1, negative. -5 minus 3, negative. -5 plus 4, negative. So if I have a negative times a negative times a negative, negative times negative times negative, I get a negative. Is a negative greater than or equal to 0? No, that's false. So don't trade in region 1. Region 1 is left. Unshaded. And do the same thing for all these. -2. -2 plus 1, negative. See, I don't care about the exact value. I just want the sign. That makes it much, much easier, right? -2 minus 3, negative. -2 plus 4, positive. Okay? I only want the sign. I don't care about the exact value. So what do you get when you have a negative times a negative times a positive? Negative times negative times positive. Is a positive number greater than or equal to 0? Yes, that's true. Shade in region 2. Okay, region 3, 0. 0 plus 1, positive. 0 minus 3, negative. 0 plus 4, positive. So I have a positive times a negative times a positive. That gives me a negative. Is a negative greater than or equal to 0? No, it's not. False. So do not shade in region 3. And finally, region 4, plug in 4. By the way, here's the reason why I write Roman numerals. Roman numerals. Okay, not the usual 1, 2, 3, 4. See, if I put regular 1, 2, 3, 4, there's a 4 here, then there'll be a 4 here, right? Say, huh? Is this 4 or that, right? So to make sure I don't get mixed up, the Roman numeral 1, 2, 3, 4, say, okay, I know I'm not doing the number 1, 2, 3, 4. Suppose I put the regular 4. This is the Roman numeral 4, right? If I put a 4 here and there's a 4 here, you might get mixed up and say, how come there's a 4 here and a 4 here? So, no, that's the region 4. That's the number 4. So to avoid all that complication, I use Roman numerals for the region. So region 1, 2, 3, and 4 means I'm not using the number, although in this case, yes, I am plugging in the number 4, and that avoids any confusion. Okay. All right, supposedly they're all positive. Let's check. 4 plus 1, positive. 4 minus 3, positive. 4 plus 4, positive. They're all positive. Positive times positive times positive is a positive. Is a positive greater than or equal to 0? That's true. Shade this one in. And yes, you say, hey, this one does alternate. Yes, it did happen a lot. In fact, I would just say maybe more than half the time. More than half the time when you have problems like this, they will alternate. Okay, but you shouldn't trust in that. Okay, because some of you were trying to say, oh, this one's false, right? So I know automatically this one's true, this one's false, this one's true. That happened to work, that scheme worked for this one, and that happened for a lot of them, but that wasn't going to work for this one, right? So I guess if you plan on using that scheme, you're right that it happens more often than random, where you just say, okay, once I find this one, I'll just alternate. In other words, if this one was false, right? You say, okay, that one's going to be true, this one's false, this one's true. It seems like that happens all the time. It does not happen all the time. It did not happen over here, but it does happen a lot, is maybe the best way to say it. All right, so I'm done. So I write bracket -4, -1. This time I have to write union because there's two separate regions. I didn't have to do that over here, but over here I will. So bracket -4, -1, union bracket 3, infinity. And remember, bracket means you include the endpoints. Parentheses means you don't include the endpoints. And positive infinity is always on the right side. Negative infinity, if we ever use negative infinity, is on the left side. And they always use parentheses because you don't reach infinity. You don't reach negative infinity. Okay. All right, so I was going to stop there. I'll just mention quickly tomorrow, when I continue, we'll have fractions again. Okay, so the ones I showed you today didn't have fractions, but these have fractions. And one sneaky thing about fractions is you could have one closed and one open, which is exactly what happens over here. Okay, and how do you have one open and one closed? Okay, part of the reason is, remember, you're not allowed to divide by 0. Okay, well, even over here, if you take a look, what happens if you try to plug in -3, right? You'd have -3 plus 3, which is 0. And yes, you cannot divide by 0 on the bottom. Okay, so same thing, though, in principle. If you were to say to yourself, I'm taking the square root of something, even if it's a fraction, that whole thing has to be greater than or equal to 0. So I would set that thing greater than equal to 0. Okay, so I'll show you that starting tomorrow. And then, yeah, you would set the top equal to 0, set the bottom equal to 0. So give you a heads up, it just save me some time for tomorrow. So what number makes the top 0? 1. All right, what number makes the bottom 0? -3. So set the top and the bottom equal to 0, and then go from there. All right. Okay, but for now, I'll stop. Go from there. Let me check the chat. Okay. Let's see. All right, so we do have some questions. Let's see. 3.5. Yeah, so 3.5. So the best way I can explain it is the original assignment was 1 to 31 odd. Don't do 11. Don't do, maybe I can say I'm wrong. Don't do 23, 25, 27, 29, and 31. So the last one you need to do from 3.5 would be 21. How's that? Okay. So that's the way that works. Okay, so we do have a request from somebody, 3.4, number 27. Okay, so we'll try that. We're still recording, by the way. 3.427. All right, so let me get some paper here. Exactly what we got. Okay, that's a good one. In fact, it may even take the rest of the class period to do this one. All right, so 3.427. Write that down. F of x is equal to. Yeah, some of these problems do take a while. X squared minus x minus 2. X squared minus 2x minus 3. Okay, so let me switch back to sharing my screen. All right, sketch, do asymptotes, intercepts, and all that good stuff. All right, so it looks like we're going to do some factoring. X, 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 x. Okay, how do I get 2? 1 times 2. How do I get 3? 1 times 3. And let's see, we want to end it with a minus, so the minus should go with a larger number. And this one you want to end it with a minus, so the minus should go with a larger number. Aha, and we do get a cancellation. So it's x minus 2 over x minus 3, provided x is not equal to negative 1. Okay, so I'll graph this whole thing, but throw out negative 1. Now, what would I get if I plugged in negative 1? That would be negative 3 over negative 4, which is positive 3/4. There's a hole there. There's going to be a hole for this one. All right, so if I factor that correctly, x plus 1, x minus 2. All right. So vertical asymptote, x equals 3. So x equals negative 1 does not qualify as a vertical asymptote because I canceled it out. Instead, there's going to be a hole in the graph. So I'll graph this whole thing and then put a hole there. Okay, intercepts. What happens when x is 0? What happens when y is 0? And yeah, it's okay to go to here now because I don't have to worry about this. Okay, what happens when x is 0? Put a 0 there and a 0 there. It's negative 2 divided by negative 3, which is a positive 2/3. If y equals 0, remember y equals 0 means the top is 0. Ignore that. So how do I make the top 0? 2. 2, 0. Then for horizontal asymptotes, okay, you can either do this one or this one's probably easier, but in any event, this was the original. All right. So the game you play again is that don't even look at anything after the leading term. Okay. So x squared, just ignore this, kind of cover them up like that. And what's x squared divided by x squared? 1. So y equals 1 is a horizontal asymptote. Notice you could have done that over here also. For super, super big x, ignore these, x over x, you have 1. When you think of the logic, if I plug in a billion take away 2 divided by a billion take away 3, it's basically a billion divided by a billion, which is 1. Right? If someone's a billionaire, you take away $2, they're still a billionaire. Or you take away $3, they're still a billionaire, right? It's peanuts to them, so-called. Okay, so we have this and we have this. Okay, so now we're ready to analyze. This is my vertical asymptote. So that means when x approaches either infinity or negative infinity, I'll put plus or minus infinity, y approaches 1. Okay, so I plug in a million, the ratio is 1. If I plug in negative a million, the ratio is also 1. Now I'm going to get real close to the asymptote, x equals negative 1. So I need to say x approaches negative 1 from the left, x approaches negative 1 from the right, and what happens? And I'll do a sign chart again. Oops. I'm sorry. I'm supposed to approach 3. Right, the vertical asymptote is 3. Okay, so my bad. This should be a 3. Make that a positive. Sorry, it's supposed to be a 3. All right, so 2.9. 3.1. Okay, 2.9 minus 2 is positive. 2.9 minus 3, negative. Y approaches negative infinity. 3.1. 3.1 minus 2, positive. 3.1 minus 3, positive. Positive divided positive, positive. Y approaches infinity. Okay. So I try to put all the pieces of the puzzle together, and now I'm ready to graph it. Vertical asymptote at x equals 3. 1, 2, 3. Horizontal asymptote y equals 1. 0, 2/3. 2, 0. This almost tells me already what's happening. I'm going to go down here and over here probably, right? So when I approach 3 coming from the left side, I drop to negative infinity. When I go way out to the left, I get close to y equals 1. And then I have to remember I punch a hole at negative 1, 3/4. So very crudely, there's a hole there. When I plug in negative 1 right here and here, that gave me negative 3 divided by negative 4, which is positive 3/4. Okay, and what happens on this side? If I approach 3 coming from the right, it shoots up to infinity. And then on this side, I get real close to y equals 1 again. So there's my graph. Like that. Okay. So summarizing all this. So first factor, cancel x plus 1. So this is the function as long as x is not equal to negative 1. Okay. So I can plug in negative 1 here. I got 3/4, but I cannot plug in negative 1 here. That leads me to the hole right there. The vertical asymptote, x equals 3. Horizontal asymptote. Okay. From here, just take the leading terms, cover these up. X squared divided by x squared, 1. Or you could do this one also. Cover these up, x divided by x, 1. So y equals 1 is a horizontal asymptote. Okay. Then I saw what happened when I approached 3 coming from the left. It went to negative infinity. When I approached 3 coming from the right side, positive infinity. That goes toward 1. That goes toward 1. Okay. So that's that. Okay. Check the chat. Somebody asked for 3.443. Okay, let's see if I can start that. All right. We may not finish early after all, but that's okay. Hey, the main thing is you guys are learning stuff, right? You shouldn't feel like, oh, I just want to leave early every day. You know, the main thing is you get your education, right? X squared minus 5x plus 6. Okay. All right. Yeah, this one will almost guarantee that I don't finish early. Sorry. X squared over 2, x minus 3. Okay, so intercepts. When I plug in 0, I get 0. So it goes through the origin. Vertical asymptote. X equals 2. X equals 3. Horizontal asymptotes. X squared divided by x squared is 1. Or equals 1. See, for x is real big. If I plug in 1,000,000, these two drop into insignificance. 1,000,000 squared over 1,000,000 squared minus this puny number, quote unquote, and 6 the puny number that time. It's basically 1. Okay. So there we go. So the main thing now is the sine analysis. Let me see if I can get that to you. 1, 2, 3. Okay, vertical asymptote. Vertical asymptote. X equals 2, x equals 3. Horizontal asymptote, y equals 1. Touches the origin and nowhere else. Okay. I'm going to copy I got it up here, but I'm going to copy it here. F of x equals x squared over x minus 2, x minus 3. And do my sign analysis. Okay. This almost tells you what to do. It looks like it's going to go here, right? The way it's going. But we better make sure. All right, so I have this and this. Okay, so I need to approach 2 from the left and right, and 3 from the left and right. So x approaches 2 from the left, x approaches 2 from the right, x approaches 3 from the left, x approaches 3 from the right. Okay, and then do a sign chart. So you have to think of a number. Okay, so I'll put it on this side this time. So 1.9, 2.1. A little bit to the left of 3, 2.9, 3.1. This will make things easier. What do you know about x squared? Always positive, right? Plus, 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 plus. What time is it? We're not finishing early at all. Okay. So 1.9 minus 2, negative. Uh, 1.9 minus 3 is negative. Right? So that makes the whole thing positive. So y goes to infinity. Like that. And we already know over here it's going to get close to the asymptote. Okay, 2.1. 2.1 minus 2 is positive. 2.1 minus 3 is negative. Negative. Y approaches negative infinity. 2.9. We already know this is positive. 2.9 minus 2, positive. 2.9 minus 3 is negative. Again, negative. Y approaches negative infinity. Okay, so this thing just goes up somewhere and comes back down. It doesn't touch the x-axis because we already got all that. And finally, 3.1. 3.1 minus 2, positive. 3.1 minus 3, positive. Everything is positive. So y approaches infinity. Okay, so that does it. On this side, we go toward infinity. And then over here, we approach the asymptote. That's what we have for the graph. All right. Go through again. But this is still recording. So here's the bottom part, middle, and top. All right, folks, that'll do it for today. I guess we didn't finish early, but that's okay. It's more important to get your education right. Okay, so that'll do it, and we'll pick up from here tomorrow. All right, have a good day, everybody. Bye.